What's up, Calc Gang? Welcome back to some physics. So we're solving this problem here where we have this archaeologist that's on a rope crossing between two cliffs. So it tells us that he stops to rest in the middle, and then the rope, it tells us this tension that the rope that'll break once it exceeds that force. And we're also given the hero's mask. So first of all, let's solve part A. So let's see, part A right here. We want to find the tension in the rope. And that is given us the information that the angle of the rope is 10 degrees and the mass is 90 kilograms. So this is the mass of the archaeologist, right? So when we're solving a problem like this, right, we're trying to find tension. We're going to want to start with a force body diagram, right? Because we have different forces. So looking at this picture, this archaeologist weighs 90 kilograms, so he's going to have a force of gravity, right? That's going to be pulling him down. And what's going to be holding him up is that tension. So let's see. So I went ahead and drew a force body diagram. Let's look at it. Here it is, right? So of course, this is at the center of the rope where our archaeologist is. This is where that center is. Force of gravity is pulling down. That makes sense because force of gravity always pulls towards the center of the earth. Now we have these two tensions, right? We're told we're in the center of the rope. So these tensions are going to be pulling away at the direction of the rope. And we know that that angle is going to be theta, which is 10 degrees in this case, above the horizontal. Just you can tell by similar angles. From the image, it shows it on the top side. So this is going to be the same angle. So this force body diagram is nice, but what are we going to do with it? Well, let's go ahead and try to solve. So first of all, we need to turn this into, just looking at it, to a mathematical equation of some sorts. So let's analyze the text a little bit. So in the book, it says he stops to rest. Now, when you hear rest in any form, that implies that you're not moving and you're not accelerating. So in that case, we know that acceleration in the x direction is 0 and acceleration in the y direction is 0. And by this equation, right, Newton's law, force is equal to mass times acceleration. If acceleration is equal to 0, this is going to all become 0 and force is going to be equal to 0. So if we're not moving, we know that the sum of the forces in the x and the sum of the forces in the y are going to sum up to 0. Now this is going to be the most important equation right here. These two, sum of the forces x is 0, and sum of the forces in the y is 0. So how are we going to do this, right? Well, we need to go ahead and add up, basically. But first of all, when we have forces in the x and the y direction, we need to convert our vectors into x and y. So to do that, I'm going to go ahead and I'm going to draw one of these tensions as a triangle. So what I'm looking at is tension 1 here, right? I redrew it just in a little bit bigger. So tension 1, it has that angle, right? 10 degrees. But what I went ahead is I made this a right triangle. So I broke up tension 1 into tension 1 in the x direction, which is just this arrow that points along the x direction. And I also broke it up into tension 1 in the y direction, which is just this vertical arrow, which points, from 0 to the top. Now, because we have a right triangle, whenever we sum up the forces in the x direction, we can't just do tension 1. We need to do tension 1, but only as much as it acts in the x direction. And to do that, we need to figure out what exactly that is. So we're going to use SOHCAHTOA, right? So SOHCAHTOA is this, right? Sine, opposite, hypotenuse, et cetera, right? So let's put this here. We're going to be trying to figure out, basically, move all this out of the way for now. We're going to try to figure out what tension 1x is and tension 1y is in relation to tension 1, because we're solving for tension 1. So let's start with tension 1 in the y direction, right? This is opposite of the theta. So if it's opposite, we're going to use sine, right? Because we know tension 1 and tension 1y. So we're going to use sine of theta is equal to opposite, which is tension 1y, over hypotenuse, tension 1. So then we can simply multiply tension 1 to the other side, and we're going to get that tension 1 sine of theta is equal to tension 1y. So this is an important piece of information. We're going to keep that over here and move this out of the way. So let's do the next one, tension 1x. So tension 1x is this vertical part, this horizontal part, excuse me, and this is adjacent to that theta. So that means we're going to use cosine of theta because it's adjacent hypotenuse. So cosine of theta is going to be tension 1x adjacent divided by tension 1, which is the hypotenuse. Then again, we're going to simply multiply that tension 1 on the denominator over to the other side. to get tension 1 cosine of theta is equal to tension 1x. So let's move this out of the way now that we've solved that. And we have these two equations, which are very handy. Tension 1y and tension 1x are equal to, they're basically, you can always think about it like this, and soon this will become very intuitive. But tension 1y is always tension 1 sine of theta. It's going to be a relation, basically something less than tension 1. So now that we have these two numbers, let's move on to trying to solve this. So let me get this out of the way too. We have this, and we have these equations again, right? Force of sum of the forces in the x is equal to 0, and sum of the forces in the y is equal to 0. So let's start with the sum of the forces in the x is equal to 0. So by alone, this equation doesn't look that handy, but what we're going to do is we're going to sum up all of the forces in the x direction in this force body diagram. So looking at this force body diagram, what's acting in the x direction? Well, force of gravity is only acting in the y-axis. So force of gravity is not going to be in the x equation. But tension 1 and tension 2 are both pulling left and right in the x direction. So looking at that equation, let's expand it, right? Instead of sum of the forces x, we're going to replace it with the sum of the forces. So tension 1 pulls negative in the x direction, so we have to subtract tension 1. And then let's specify that this is tension 1 in the x direction, because tension 1 acts at an angle. So we can't say all of tension 1 acts in the x direction, only some of it. And that's where this is going to come into play. Right. And so then we have this equation. So negative tension 1, x is pulling left, positive tension 2 is pulling right. So we can simplify this equation. Let's go ahead and add tension 1 to the other side. Or basically, we're just making this equal to each other. So tension 1x is equal to tension 2x, which makes sense, right? Because he's in the center of the rope, they're going to be equal. So what we're going to do now is we're going to expand, right? What we said earlier is we don't want tension 1x because that's not specific. We want it in terms of just tension 1. So we found earlier that tension 1x is equal to tension 1 cosine of theta. So what I did here is I went ahead and replaced tension 1x with tension 1 cosine of theta. Right? This and this just came together to create this. So now we have that tension 1 cosine of theta is equal to tension 2 cosine of theta. And what can we do here? Well, cosine of theta and cosine of theta, those are going to cancel out. So we're going to end up with just tension 1 is equal to tension 2. Now, that is something that we probably could have intuited, but now we're on the right direction and we know that this is true, that tension 1 and tension 2 are equal to each other. Right. So let's go ahead and move on. So we have this information, which is going to be useful. Let's try our next equation, right? We did sum of the forces in the x is equal to 0, and that left us with tension 1 is equal to tension 2. What can we do next? Well, let's do sum of the forces in the y is equal to 0. So we're starting with sum of the forces in the y is equal to 0. I'm going to put this up here because this is a good piece of information to have. Sum of the forces in the y is equal to 0. So let's look at a force body diagram. Well, what do we have? Tension 1 and tension 2 act at an angle, so of course they're pulling in the y direction too. They're pulling up in the y direction. This is why the archaeologist doesn't just fall down. It's because the rope is pulling up at some amount. So we have tension 1 y and tension 2y, but then we also have force of gravity pulling straight down. So this is what our equation is going to look like. Tension 1y is pulling up, plus tension 2y is pulling up, but force of gravity is pulling down, so we need to subtract it. So then, let's go our next step. So we're going to do a very similar thing, right? We don't want tension 1y, we want tension 1. So what do we found earlier that tension 1y is equal to? We found tension 1y is equal to tension 1 sine of theta. So in this step, I went ahead and I said tension 1 sine of theta plus tension 2 sine of theta, and then I added the force gravity to the other side. So tension 1 sine of theta plus tension 2 sine of theta is equal to force of gravity. From here, I went ahead and expanded force of gravity, right? Force of gravity is equal to, this is Newton's law, force is equal to mass times acceleration. When we're looking at force of gravity, its force is equal to mass times the gravitational constant, which is the constant acceleration that you experience on Earth, which we label just g. So this is the same thing, but, right, mass gravity is replacing force of gravity. Now, also, this is where this becomes very useful, right? Remember we found that tension 1 is equal to tension 2? Well, we don't want 2 unknowns in our equation. We want to simplify it just down to 1 unknown. So here we had tension 1 and tension 2. What I did is I went ahead and replaced tension 2 with a tension 1 because we know that they're the exact same value. So now we're left with the simple equation, tension 1 sine theta plus tension 1 sine theta is equal to mass gravity. And of course, because these two are the same, we can combine them into just 2 tension 1 sine of theta is equal to mass gravity. Now, right, we know most of these things. What are we solving for again? We're solving for tension. We know theta, we know mass, and this gravitational constant we know. So all we need to do is rearrange this equation with a little algebra. So what I did here is I divided both sides by 2. This got rid of the 2 on the tension side and put a 1/2 on the mass gravity side. Next, I'm going to divide by sine of theta to get tension 1 is equal to 1 over 2 sine theta mass gravity. Move all this up. All right. Then we can plug in our numbers. So let's plug in our numbers. Oops, it's getting a little cramped in here. Right, so we know that theta is equal to 10 degrees. Make sure that your calculator is in degree and not radian mode. Mass is 90 kilograms. That's the mass of the archaeologist. And gravity is that 9.81 constant. So if you solve this, you're going to get that tension is equal to 2,540 newtons. And so this is tension 1. Well, we know that tension 1 is equal to tension 2. So basically, we just know that the tension is equal to this number. All right, so that's the step to part A, right? We found tension. Tension is this. So excellent. Let's go ahead and get rid of this all that I don't need. I suppose this is all good to go. Hopefully I don't need any of that because it's all in a pile now. All right, so part 2, right? We're moving on to part B. I want to keep all this stuff on the page. It's all kind of useful. All right, part B is asking, if tension cannot exceed 2.5 times 10 to the 4th newtons, right? So scientific notation, we're looking for the smallest angle possible that allows the tension not to break. So the reason this is different, right, is we know tension, what am I saying? Right, tension is going to get bigger as this angle gets smaller. Now that might not be intuitive, but as we basically imagine a really slack rope, like you're hanging vertically, it's going to just be holding all of your weight. But if you look at that archaeologist, he's holding a lot more weight on the tension, right? The tension is going to be very tight the smaller that angle gets. So at some point, this angle is going to get so small that the tension is going to break and it's going to go past this number. So the method we need to do is we're basically going to solve backwards for theta by inserting that tension 1 is equal to 25,000 newtons. So we're basically doing the same steps, we're just given a different known this time. So we're going to start again with that sum of the forces y is equal to 0. So I'm going to get rid of this. Sum of the forces y is equal to 0. And again, it's going to be the same thing, right? Tension 1y plus tension 2y minus mass gravity is equal to 0. This is the exact same step we did last time. Then again, I'm going to insert all these things. So I'm doing the exact same steps we did last time. Inserting tension 1y into tension sine, and then moving that mass gravity over. What's going to happen here, again, that tension 2 is going to become tension 1 because they're equal to each other. And we're going to be left with 2 tension 1 sine of theta is equal to mass gravity. Then again, now, instead of solving for tension, we know what tension is. We're solving for theta. So what I did is I divided by that 2 tension to leave theta, or the sine of theta, by itself on the left side of the equation. Then, to isolate that theta, I took the inverse sine of both sides. And that inverse sine is going to cancel out that sine, and it's going to be left with theta is equal to inverse sine of mass gravity over 2 tension 1. Then all we got to do is plug in our numbers. So theta is equal to inverse sine of mass, which is 90, gravity 9.81, over 2 times the tension. So the tension maximum is that 25,000. So that's what I inserted for tension 1. Now plug this into your calculator, and you're simply going to get that theta is equal to 1.01 degrees. So that's how we solve part B of this problem. Smallest theta possible is that 1.01 degrees. Anything smaller than that, and the rope is going to break. So that's how you solve this problem. Thank you for watching. Appreciate it. Check out my playlist for more physics videos, and I'll see you in the next video. Peace.